For millennia, humanity has gazed upwards. We looked at the stars, the moon, the sun. We noticed points of light that wandered. These were the planets, the wanderers of the ancient sky. Early astronomers tried to make sense of their movements. They built elaborate models. Most of these models placed Earth at the center of everything. This was the geocentric view, a comfortable idea for many centuries. The most famous of these Earth-centered models came from Ptolemy. Around the 2nd century AD, he described a system of circles. Planets moved on small circles called epicycles. These epicycles in turn moved along larger circles called deferents. This system, while intricate, did a decent job of predicting planetary positions for its time. It held sway for over 1,000 years. Then came Nicholas Copernicus in the 16th century. He proposed a radical shift in perspective. Copernicus suggested that the sun, not the Earth, was at the center. This was the heliocentric model. Earth became just another planet, orbiting our local star. This was a monumental change, a demotion for Earth perhaps, but it offered a simpler, more elegant explanation for the apparent motions of the planets. Johannes Kepler arrived on the scene in the late 16th and early 17th centuries. He was a German astronomer and mathematician. Kepler was a fascinating figure, deeply religious yet fiercely committed to empirical observation. He believed that God had created the universe according to a divine, mathematical plan. His life's work became a quest to uncover this cosmic blueprint. He wasn't just content with models that predicted where planets would be. He wanted to know why they moved as they did, to understand the underlying physical laws governing their celestial dance. Kepler's big break came when he began working with Tycho Brahe. Tycho was a Danish nobleman and astronomer. He had amassed the most accurate and extensive set of naked-eye astronomical observations ever made. Tycho's data on planetary positions, especially for Mars, was unparalleled. When Tycho Brahe died in 1601, Kepler inherited this treasure trove of observations. Kepler focused particularly on the orbit of Mars. Mars was a troublemaker for astronomers. Its orbit was notoriously difficult to reconcile with existing theories, including Copernicus's circular orbits. After years of struggle, Kepler finally cracked the Martian code, and in doing so, he unlocked the secrets of planetary motion for all planets. This relentless pursuit of accuracy, this refusal to accept a good enough solution was Kepler's genius. Kepler's first major breakthrough, born from his struggles with Mars's orbit, was revolutionary. He announced it to the world in his 1609 work, Astronomia Nova. This is Kepler's first law of planetary motion. It states that planets move in elliptical orbits, not perfect circles, and the sun is not at the exact center of this ellipse. Instead, the sun resides at one of the two focal points, or foci, of the ellipse. This was a radical departure from millennia of astronomical thought, which had always favored the perfection of circles for heavenly movements. Imagine an ellipse. It's like a squashed circle, an oval shape. You can draw one with 2 pins, a loop of string, and a pencil. The pins are the foci. The string, kept taut, guides the pencil to trace out the ellipse. For planetary orbits, the sun sits at one of these pin positions, one focus. This means a planet's distance from the sun changes as it moves along its orbit. Sometimes it's closer to the sun and sometimes it's farther away. This variation in distance was a key insight that helped explain the observed changes in planetary speeds, something circular orbits couldn't easily account for. The ellipse itself naturally accounted for these variations. This discovery was not just a mathematical trick, it described the actual physical path planets take through space. So, what exactly is this ellipse that planets trace? It's a specific type of oval, a conic section. You get an ellipse if you slice a cone at an angle. Circles are also conic sections formed by slicing a cone horizontally, but ellipses are more general. An ellipse has 2 special points inside it called foci, plural of focus. The sum of the distances from any point on the ellipse to these 2 foci is constant. This constant sum is what defines the shape and size of the ellipse. For planetary orbits, the sun occupies one of these foci while the other focus is empty space. The degree of squashiness of an ellipse is described by its eccentricity. Eccentricity is a number between 0 and 1. An eccentricity of 0 means the ellipse is actually a perfect circle. Its 2 foci merge into a single point at the center. As the eccentricity approaches 1, the ellipse becomes more and more elongated, almost like a very thin cigar. Most planets in our solar system have orbits with fairly low eccentricities. This means their orbits are very nearly circular, but not quite. Kepler didn't stop with just defining the shape of planetary orbits. He also figured out planets move along these elliptical paths. This led to his second law of planetary motion, also published in Astronomia Nova in 1609. This law is sometimes called the law of equal areas. It states that an imaginary line joining a planet and the sun sweeps out equal areas during equal intervals of time. This might sound a bit abstract at first, but it has a very important consequence for how fast planets travel in their orbits. It means planets don't move at a constant speed. When the planet is closer to the sun, near perihelion, the line connecting it to the sun is shorter. To sweep out a certain area in a given time, the planet must travel a longer arc length along its orbit. This means the planet moves faster when it's closer to the sun. Conversely, when the planet is farther from the sun, near aphelion, the line connecting it to the sun is longer. So the planet moves slower when it's farther from the sun. Kepler's quest for cosmic understanding didn't end with his first two laws. He was searching for a deeper harmony, a mathematical relationship that connected the different planets in the solar system. He found it a decade later, publishing his third law in 1619 in his work Harmonices Mundi, The Harmony of the Worlds. This law establishes a precise mathematical link between a planet's orbital period, the time it takes to go around the sun once, and the average distance of its orbit from the sun, specifically its semi-major axis. Kepler's third law states that the square of a planet's orbital period, let's call it p, is directly proportional to the cube of the semi-major axis of its orbit, let's call it a. Mathematically, this can be written as p squared is proportional to a cubed. This means if you know how long it takes a planet to orbit the sun, you can figure out its average distance from the sun, and vice versa. Consider the planets in our solar system. Mercury, the closest planet to the sun, has a short orbital period of about 88 Earth days and a small semi-major axis. Earth has an orbital period of 1 year, about 365.25 days, and its semi-major axis is defined as 1 astronomical unit. Mars, farther out, has a longer period of about 687 Earth days and a larger semi-major axis. Jupiter, much farther still, takes nearly 12 Earth years to orbit the sun. Kepler's laws provide a deep understanding of planetary motion, including their speeds. While Kepler's second law tells us that a planet's speed varies, faster when closer to the sun, slower when farther away, we can also think about its average orbital speed. For an orbit that is nearly circular, or if we are interested in an average value, we can make a straightforward calculation. The journey a planet takes in one orbit is roughly the circumference of its orbital path. The time it takes to complete this journey is its orbital period. Speed in its simplest form is distance divided by time. So, for a planet in a roughly circular orbit of radius r, the circumference is 2πr. If its orbital period is p, then its average orbital speed v can be approximated as v is approximately equal to 2πr divided by p. This gives us a good sense of how fast planets are cruising through space. For Earth, with an average orbital radius of about 150 million kilometers, 1 astronomical unit, and a period of 1 year, this calculation shows our planet is constantly moving at an astonishing speed of roughly 30 kilometers per second, or about 107,000 kilometers per hour. That's incredibly fast, yet we don't feel it because everything around us is moving along with the Earth. Mercury, being closest, zips around the sun at an average of 47 kilometers per second. Kepler's laws were revolutionary. They described how planets moved with unprecedented accuracy. But they didn't explain why planets moved in this way. The answer came with Sir Isaac Newton. Newton formulated the law of universal gravitation. He showed gravity keeps planets in orbit. This force was gravity, an attractive force between any two objects with mass. Johannes Kepler's laws remain fundamental in astronomy and astrophysics today. Engineers use Kepler's laws to calculate spacecraft trajectories and orbital insertions. These laws enable our exploration of the solar system. Kepler's laws apply to planets, moons, and artificial satellites. They even govern binary star systems. Kepler's laws are crucial for detecting and characterizing exoplanets. They help us search for habitable exoplanets. Kepler's legacy is one of mathematical rigor and respect for observational data.